My name is Lee. I'm a principal solutions architect with our Amazon Omics product team. I've been at Amazon for about just over 5 years, and for almost the entirety of that time, I've been focusing on solutions in the genomics and life sciences space. And today, we're going to cover how to use one of our services, so Amazon Omics, to go end-to-end from raw sequence all the way to querying variants. And for folks that are here, I want to stress that this is going to be some hands-on learning. So if you have a laptop, open it up, get ready to get some hands-on keyboard. I'm going to cover just a couple of slides first, and then we're going to really get into it. I'm also going to, later in the talk, we're also going to be joined by a partner of ours. We have a couple of speakers from BioTeam that'll talk about how to use Amazon Omics further from experiences they've had out in the field as well. So I just went over this, but this is the agenda. I'm going to give you a little bit of background. I'm going to introduce you to what Amazon Omics is for those of you that have never touched it before. Actually, show of hands. How many people, one, know what AWS is? All right, two, know what Amazon Omics is? All right, or just here for the stickers? Okay, we're good. All right, so we're going to introduce what Amazon Omics is. We're going to do that hands-on learning. So laptops out. Stress laptops. This might work on an iPad. I haven't tested that out, so good luck. And then we'll have a little bit of commentary from BioTeam, and then wrap it up with some resources to learn more. All right. So I like to level set for folks that might not have raised their hands as to what AWS is. AWS is a cloud computing service provider. And so you can think of AWS kind of like a public utility, but for computers. So you get computers that are on demand, fit for purpose. They come with pay-as-you-go pricing, and you use only what you need at that moment in time. And so what that allows you to do is to focus in on just building applications that work in the cloud. And speaking of what that cloud is, it is a global footprint overall we have 31 regions and 99 availability zones. You can think of an availability zone like a group of tightly coupled data centers. And most AWS regions around the world have at least 3 of those. And our capacity is always growing. And so we've recently announced plans for 12 additional availability zones and 4 more regions in Canada, Israel, New Zealand, and Thailand. And overall, what AWS provides for you with this global footprint and effectively utility computing is these 5 core benefits. So we have infrastructure that has been custom built and designed to meet the most stringent security requirements in the world. And all of the applications that you can build on AWS can be spread across multiple availability zones and regions, so you can provide applications with high availability. AWS offers low latency, low packet loss, high overall network quality, and a wide variety of instance types. So you can select what you need to meet your performance criteria. And then all these applications can be dynamically scaled to meet your demands, your customers' demands for your applications. And that means you have the flexibility to build and run applications that meet your differentiated requirements. And all this is all offered at low costs. So where does genomics come into all of this, right? Well, we've talked with a lot of customers over the years, and we know that from your perspective and the perspective of the world, that genomics and biological data have the potential to transform how we treat disease. But it's pretty complicated, right? We've heard from a lot of folks that there are common challenges. They keep coming up over and over again. For instance, you need optimal ways to store all that genomic data. You have that are cost efficient, easy to access. You also need tools to analyze trends across millions of individuals, perhaps train ML models. And then you need to scale that compute across millions of biological samples while preserving accuracy, reliability, and managing costs, as well as security, because a lot of this stuff is pretty personal. It is your source code, so you do need to keep security, compliance, and privacy in mind. And what's really driving this is, I like to show this chart. This is the cost of genomic sequencing for a human genome for the past roughly 20 years. It started out at almost, what is this? I can't see on the screen. Almost 100 million. And now it's roughly $200. So that means that it is, it's a lot easier. It's a lot more cost affordable to get a whole sequence. And that also means that data is coming out perpetually. So you're getting terabytes of data, possibly on a daily basis, from your own core sequencing facility. All right, and so with all of this as a backdrop, this is why we built Amazon Omics. We launched it as a purpose-built service that helps healthcare, life sciences organizations, companies, folks like yourself, to store, query, and analyze genomic, transcriptomic, and other omics data. And then you can then generate insights from that data so that you can improve health and advance scientific discoveries. So overall, we have a core set of benefits. You can use omics to generate multi-omic and multimodal analyses, so you can securely combine genome of individual genomic data from individuals with, say, their medical history to offer more personalized care. You can use purpose-built data stores to support large-scale analyses and collaborative research across whole populations. Or you can accelerate research using automated workflows and integrated computational tools. And finally, you can protect all of that information with GDPR-ready compliance and HIPAA eligibility. All right, so how does this work end to end? Simply put, you start with raw sequence, you store it in, say, sequence or reference stores, you process that data using workflows, and latest feature that we recently announced is ready-to-run workflows. So you can bring your own private workflows that you've designed yourself, or you have a selection of out-of-the-box, ready-to-use workflows that are available at effectively the push of a button. And then from those workflows, say you generate interesting features. So in the genomic space, we call these variants. You can take those variants, you can store them into analytic stores that you can then query for further insights. And then those queries can be combined with other modalities, so things like medical imaging or health records. And you can use all of that to create a more precise view or a more global view of your samples and your data. From the builders in the room, this is what it looks like. The stack is effectively three fundamental services. There's storage. So we have storage that is aware of what a genomic sequence is. We have compute, so bioinformatics ready compute in the form of workflows, and then analytics. So things like databases, things you can think of like a database for storing your variants. And all of these are things that you can use to build your applications. Okay, so what are some of the top use cases? You can use it for whole population scale sequencing. So you can analyze thousands of genomes at once to understand how genomic variation maps across phenotypes across a population. You can use it to improve clinical genomics workflows. So you can build reproducible and traceable workflows from raw sequence data to something that applies to, say, your clinical or translational research. And then that helps you to accelerate your clinical trials. And then finally, more broad spectrum, you can use this as a fundamental building block to enhance and advance your research. All right, I'm done talking. So now I want to start building. So this is the point in time where we are going to get our laptops out, and we are going to do exactly this. So we're going to take some raw sequences, we're going to put them into omics storage, and we're going to run some workflows. A couple of workflows will operate on those raw sequences that you store into omics storage, and then from those workflows, they will generate VCF files, which are what a typical format for storing variants. We'll take those variants and we'll put them into an analytics store, and then we'll query those. Part of the data sets that we will use come from our open data program. So I want to highlight that just real briefly. The registry of open data exists to help people discover and share data sets that are available via AWS. So all of these things can be accessed through AWS native interfaces like S3 buckets, SNS topics, RDS snapshots, shared EBS volumes. And the whole point of this is to make data that is through whatever service that makes the most sense for the community of users. And the importance is we don't want data access to be a blocker. We want folks to readily access data and get their research done and find the insights that they need to use. So we're using some data sets associated with this program. If you want to learn more about this, if you have important data sets that you want to share with your collaborators, highly recommend. We actually have a representative in the back. She's waving. Anyway, speaking of other folks in the room, I am joined in this room by a couple of folks. If you all want to raise your hands, I've got Doman in the back there. He's a PM for Omics. We've got Mark and Nadeem. They're SAs, solutions architects that I work with on the regular. They are going to be floating the room to help you out on the hands-on portion. I'm also here with a couple of folks from BioTeam. So we have Carl and Bill, also from BioTeam, who will also help out in the room and come up and speak at the end of the hands-on stuff. Okay, so let's get going. What we're going to use today is an environment called Workshop Studio. All you need is your laptop and a browser for this. And at this moment in time, what I'll do is I'm going to drop over to here. This is the slide you need to go to. This is the link you need to go to. So open up a browser, type in that link. That'll take you to a login page that will get you started with the workshop. For folks that don't have a laptop, buddy up. This is important for the hands-on part. The workshop material this will bring you into a workshop environment that gives you an AWS account to use for this session. You don't have to bring your own. We've provided one for you. It will have all of the resources that we need to complete this workshop. All right, I'm going to leave this up here. Does everyone have this slide or have this link? I'm seeing some heads bobbing up and down, so I'm going to presume that folks are kind of typing away at this.
The third letter is a G, not a Q.
Yeah.
It's FSG.
It's a G, and those are two O's, not a 0.
And if you're looking at the preloaded slides, you'll actually want to use the URL.
Use the URL on here. The preloaded slides were in flux, so I needed to create this account or this session effectively last night, and so I needed to update the link accordingly. So use this slide, the link on this slide. I should have about 50-ish. Yeah. Hi, Cindy.
So I'm getting pinged on my phone from the team because the workshop is of interest to so many new people.
Okay.
So I didn't want to say yes, they can go if you can't accommodate
how many people do we have in the room right now? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. About 35. Yeah, I think we can accommodate about 20-ish more.
Okay.
So.
Well, thank you. I don't want to create a situation.
Okay, so what I'm going to do is I'm going to pop out, and I am going to, let's do this real quick. Let's mirror real quick. Yep. So all of my helpers are here to help folks that have any issues. So raise your hand if you do, and folks will come around and check on you or your situation. Okay. So if you haven't got it yet, here's where you're supposed to go. What this will do is it will take you to this page. Here, what I'm going to do is drop it. So what I'm gonna walk through this. Let me blow this up a little bit. I'm gonna walk through this for you. So we're gonna go and get your one-time password. Just drop in your email. And so that'll take a couple of minutes, depending on how fast your Exchange server or your email server works. But once you get that passcode, you will drop it into here. I'm refreshing on my phone real quick. There we go. I got mine. So this is my passcode. Don't enter this. This is 576 873 50. All right. And so once you get there, you'll get to here. This should already be filled in, or not. This is my access code. For you, this should already be filled in. I don't know why it's not for me. Go on next. Okay, so this is, we'll get to here. Sorry. Sure, I'll pop back in here. I wish there was a way to just like keep this.
There's no whiteboard. We would write it down.
Yeah. Here, I'll there, that makes it clearer. So it's an F, it's a lowercase f, capital S, lowercase g, capital D, F, lowercase f, capital N, lowercase o, capital O. Everyone not get to the sign-in page. All right, so agree to the terms and conditions. Basically, this is saying.
So she's getting like access code is wrong.
Access code. I do have the right access code. So if you don't have the access code, what I'm going to do is I'm going to copy this and I'm going to put it in the slides. And I'm just going to say. This is the access code you need. Don't know why this link didn't work. All right. Yeah, we're all good? All right, so terms and services basically say, don't put any private information into these accounts. These accounts are only available during the session. Don't mine any crypto, right? And these will be terminated at the end of the session. So, all right, so go ahead and join event. And then what it'll do is it'll take you to, I did start the event. There we go. It should take you to here. And this is going to be where where you kind of launch off two things. So what I recommend is, I'm actually going to pull this out and drop this under here. So what I recommend is you do two things. You go to AWS Account Access, and I usually will open this either in a new tab or a new window. Just pop it into a new window. And so what this will do is it'll federate you into an AWS account for you to use during this session. And then, so that was right here under AWS Account Access. And then the other thing you want to do is click this button to get started. And so that'll just put you at the home page of the workshop guide. These are the materials that you'll follow along with while we're doing this, while we're operating on this workshop. And so we are going to, and if you get lost, the guide, the navigation for the guide is on the left-hand side here. So if you just click on this part right here, that'll get you to this page. And the getting started is you don't have to walk through it. We've already done most of the bits here. This is all about like how to get into here, but you're already in here, so you don't need to worry about getting into here. What we will do is we're going to drop into the console experience. There are 3 ways to do this workshop. We're going to focus on using the AWS console directly. You can also do this workshop by yourself if you wanted to with, say, the SDK. So like things like Boto 3 with Python, or using the CLI by itself. But for the purposes of what we're doing in person today, we're going to be using our mouses and clicking into the AWS console. So want to go to here, and then we will get started, effectively work through 3 sections of this workshop. We're going to work on Omics storage, Omics workflows, and then Omics analytics. And yeah, so the first thing we're going to do is, everyone here, that's a main question I have right now. Is everyone here and ready to click next and get going? I see a couple of thumbs up, thumbs up, thumbs up. Excellent. All right, so this is mostly self-guided. I'll give you a couple of like overviews of what you're going to do, but then folks are encouraged to just kind of work through the materials as they're written out. Effectively, what we're going to do for, let's say we're going to do, we're going to spend maybe about 20-ish, 30 minutes on each section. And so for this part, what we're going to work through is working with storage. So you're going to effectively take some FASTQ files and maybe a CRAM file, and we're going to import it into Omics storage. So you're going to take what is normally something that you would store just in S3 without much metadata associated with, and then we're going to put it into Omics and learn what that looks like. And then, yeah, so let's get into that. If you have any questions along the way, this guide should be here for you for the resource or instructions you need to do. Otherwise, we're floating around the room. Okay.
You have the cancer genome loaded into it.
The
cancer genome. The patient genome will have the cancer. Just to compare the
not in this particular data set, but it's something that you can bring in if you wanted to. So there are data sets like I think it's either TCGA or Nomad would probably have something like that.
And is it, can it store a lot of data like sometimes the GPs or GPs or something like that? It can load those.
Yes. So I mean, this is designed to like, so a typical human genome is about 300 gigabytes, and growing, right? So depending on what sequencing platform, what depth you want to get to. So Omics storage is designed to handle that size of data and more. So. Yeah. So we can get to that. At a high level, what you're going to do is you can have your data either in S3 or Omics storage. You can have your reference genome So part of what we do in this section is you load a reference. So it can be HD19 or HD38. And then you can take, from there, you can load in samples. In this case, I think we load in your standard NA12878. And then you'll have the data there, and then you can operate on that with compute. So that's the next section with workflows, where you take, you effectively do what's called secondary analysis and do variant calling. On the, you take the sample genome, oh boy. Okay, you take the sample genome, compare it to the reference, figure out what's different, and then after that, you can put the variant that were called from that workflow into an analytics store and compare it with, say, annotations to say.
Suppose I have my pipeline, which we are developed in the lab,
Mhm.
Will your system allow to run on your platform?
So if you have a pipeline that is already developed, so and getting a little ahead of the game, but if you have something that is written in, say, WDL or Nextflow, you can bring that pipeline or that workflow definition into Omics workflows and run it in Omics workflows. Help? Okay. So how are folks doing? I mean, what we can do is I can walk along this with you, if that would help.
That would be a good idea, because
Yep.
some people are just watching.
Yep. Why don't we do that? So what I'm going to do is I'm going to show kind of how I do this demo mode. So if you have your AWS console opened up, if you've never used the AWS console before, you might see blank here. So if you want to find Omics, you can either go to the services here and kind of scroll down and find it. The easiest way I like to do things is there's a search function up here. If you click the magnifying glass and just say Omics, it should be the first hit. And I'm going to open that up. And this lands you on what is the Omics console. So for this part, we're going to focus on storage, which is if you pop open the nav. For me, it's collapsed because I've got it on half of my screen. But if you open that up, we're going to go under storage, and we're going to go to reference store. And I'm going to close this down just for space. And so a reference store is where you put reference genomes. So these are just like raw FASTA files, is the normal format, that say this is the source code of whatever organism you're looking at. So people, mice, rats, fish. And so what we're going to do is we're going to import a reference genome in the first step here. So normally, if you've never come to Omics before, you might have to create a reference store. So we've already done that for you to avoid that confusion. But if you haven't, if you go home and want to try this on your own, you open up the AWS console, it'll probably say you need a reference store, or first step, create a reference store. But after you do that, you have your reference store. What we're going to do is click the orange button here that says import reference genome. And it already has the reference store that we have in this particular. Oh, before I forget, make sure that where you're operating in is in US East 1. So that's closest to here. That's in Virginia. That's where all the workshop stuff works in. So to figure that out, if you go up to the top here, you'll see North Virginia. If you don't, click the drop down underneath it and pick that. Okay. All right, so back where I was. Importing a reference. So what we're going to do is we're going to give our reference genome a name. So let's call this one HG19. And then we're going to, I have a link here that points to a reference that is out there in one of our public data sets. In this case, this is from 1,000 Genomes data set that was reprocessed by on import. And so this should take just a couple of minutes. But once it is done, you should have something that looks like this. So I'm just going to go back and look at a pre-imported one that is here. So this is HG38. It goes by many names. The more common one, or the more recent one, is GRCH38. And you get various details here. This is one of the the important things you might want to note is that there are a couple of URIs here that are unique to Omics. So there is this Omics URI that tells you what store it's related to and what ID this reference is. And this will come up later when we use workflows. You can actually point workflows to URIs like this to pull in the data. So you can use Omics end-to-end. All right, so that's all I want to get into. And if you wanted to, if you needed to get your reference data back out, hello, something?
Yeah, sorry, we got stopped sharing. Just give us a sec. So you can just go to big marker, please.
Okay.
Yeah. Okay. And I just need you to go to share content, please.
I don't know what happened.
And you're gonna hit blue. Yeah. Great. And you're gonna hit share. Okay. So the other thing that I noticed is that you had stopped sharing your PowerPoint slides as well. So it's just seeing you.
Yeah.
Was that your by
Yeah.
choice? Okay.
Yeah. So what I'm doing is I'm sharing my local laptop so I can demo what they're supposed to be doing. So
you want to make sure you keep the screen
Okay.
shared.
Yep.
Yep. That's the important one. People need to see things. Okay, so we're all past this. So I don't want to belabor this too much. If you wanted to, you can pull this data back out. There are ways to do it. You can do it using the CLI. There are also other tools out there to pull the data back out. But this is optional for now, and I think we should probably move on to the next parts of the course. So let's bring some actual sequences in. So things like FASTQs, SPAMs, or CRAMs. So to do that, we're going to go into back to the console here. And we're going to go under storage, and I'm going to blow this up just a little bit. Go under sequence stores. And so we can do is we can create a sequence store. In this case, you can have many sequence stores that you like. This is one way that you can use sequence stores effectively to arrange your data. So by project, by patient, or by whatever makes sense for your use case. So we'll go create a sequence store. So I got there by going to storage, sequence stores, create a sequence store. And I'm going to say my sequence store. Okay. And we're going to go create. Oh, this is new. If you get this, just say browse to S3 and just say select this bucket here. This isn't in the instruction. So we had, I'll comment that we built this workshop before some new features were launched, so there might be a couple of inconsistencies. In this case, when I create my sequence store, there's now a new option here to set an S3 fallback location. This is for a new feature we launched on yesterday. Where you can directly import sequences via a put API from your local machine. Previously, what you had to do was stage things in S3 and then import it, which is what we walk through here. So in this case, to set this fallback location, I'm going to go to Browse S3. There should be a bucket here already, so you can just go ahead and select this. And choose that. And then we will create. All right. That should be fast. And so now let's import some genomic files. So we'll click on the orange button here. And this is where references come in. So sequences don't make sense. Normally, they don't make too much sense unless there's a reference. This is also how we associate a sequence with a reference because it helps us store that sequence. That's how Omics storage is sequence aware. It helps us store that sequence more efficiently. So in this case, you can pick either one. For FASTQs, I'm going to pick the one we just imported, so HG19. So create a new service role, and in this case, we're going to use a manifest file for this. And there should be one that is documented here. So what we can do is we can right-click this button, and we'll just download this, this manifest file. Save this link as. And, oh, I already have it. Okay, so I'm going to choose that file. Downloads. And this workshop. FASTQ1. Okay, so this should, if you get that imported or uploaded correctly, you should effectively see the same thing. This is just a JSON structure or schema that says, they give some of the metadata around what you're uploading or what you're importing into Omics. So things like the sample ID, the subject ID, what sources you're importing. So in this case, I'm importing 2 FASTQ files for subject or sample NA12878. And then there are other things like where this was generated from, or and those are kind of important for folks that need to have strict provenance on their data. So I need to know that this was generated from case study 1, 2, 3, 4, 5 off of machine ABCD, so on and so on.
I have a question.
Sure.
How does resolution of reference names happen? Say if you uploaded a BAM file that was not, like the chromosome names are different compared to what your reference genome is. So it was locked in, basically.
You can do that. You might run into some issues. So Mark was going to comment there.
So yeah, you can do it.
Yeah.
So it's not equal.
Yeah. Okay, so we'll create import job. What is it saying here? This might be one of those new things that folks were telling me that. Fallback location. Hey, Doman, do you remember what the fix was for here when you import?
Yeah, you just pick. So the fallback location is part of our new release of direct upload.
So this is for the import. So that's it's asking me for S3 URI.
Yeah, so you can just pick the one
Yeah.
that gets auto-created.
Oh, this is for the service, the role access. Okay, so why don't I? What you can do is probably copy. We'll just do that. So if you say, that's right, I forgot. I'm not reading my own instructions, sorry. So when you create the new service role, this is saying, this is creating an IAM role for you. And that IAM role is basically allowing Omics to retrieve data from particular locations. And in this case, we're pulling this data from the Genome in a Bottle open data set. And so in this case, we're giving this new role that is being created on your behalf access to this S3 bucket. Sorry, getting a little mixed up today. Okay, so this will take a little bit of time. If you want to, there are also instructions, well, more or less, more a applied learning. So you can do effectively the same thing with a CRAM file if you want to on your own. And all of this is asynchronous. So while the FASTQ files are loading up, you can import the CRAM file. You don't have to wait for any of this to finish. We have things that are already, well, you do have to wait for the FASTQ files to finish, but you don't have to wait for the CRAM file to finish. We'll use the FASTQ files in the next section. So common question I get is, how do you get the data back out? Same way you would with references. You can use you can use tooling. So we have something called the Omics Transfer Manager. It's an open source tool. Or you can also hit it with the CLI to effectively pull parts of it, and then you can concatenate them back together into the full file. But you might not actually have to pull them locally. You can actually refer to the data directly from workflows, which we will touch on in the next section. All right, so is everybody with me? I see a lot of still faces. Any questions so far? Yes.
What is the benefit of using the reference of sequencing store versus
Overall, it will be easier to manage and lower total cost of ownership. So
if the reference or the sequence data is already on S3, do we have to move into the?
you don't have to. If you don't want to, you don't have to. So you can still refer to data in S3 from workflows. We built it that way on purpose because we know that there is still a lot of inertia there. So there's a lot of data still out there sitting in S3. So
The sequencing store, you have a manifest, or is it JSON YAML template? Is that, can the users define their own template in terms of giving their metadata to the reference of the sequencing store? Or
there are fields there that are required. So I think the subject and sample ID are kind of required fields. Where you do have flexibility is in the tags. So if you have your own metadata, you can put that in kind of the tag schema or section of the schema. Similar, they're similar. So they're like any AWS resource tag. So you can add them there. Mm-hmm. Okay. Let's see if this is done yet. FASTQs should take only about like 5 or 10 minutes to do. So anyway, while this is going on, you don't have to you can do things kind of in parallel. So we can probably move on to the next section for workflows while these things are importing. So next piece is workflows. So we're going to, what we're going to do here is we're going to create a couple of workflows and we're going to run them. There are some other steps that you do need to do beforehand. We've taken care of that. Mostly it's about getting the tools that you need to run in those workflows containerized and pushing them into ECR. So Amazon Omics workflows, they use containerized tools in every step. And they come from ECR. So that's how Amazon. Go ahead.
That seems like a pretty big step. You guys have like a catalog of common tools already built.
Well, that's where Ready to Run helps. So actually, I can probably show that to you right now because that's generally available. So if you go to workflows, go to the console here and under workflows, there's this brand new menu item called Ready to Run. So this is, these are whole workflows, but they do have very common tools in that we've heard a lot of customers asking for these. So we have things, workflows that are involved with protein folding. So we have tools like OpenFold and AlphaFold that are kind of baked into its own, effectively one-click workflow. And then we have other things like, let's see, these look like they're from Element. Element Biosciences is a partner of ours. They create sequencers. They have their own format that comes off of the sequencer to convert that to FastQ, that's a workflow for that. But we also have things like GETK best practices. So those would use GETK and Picard and things associated with that. Or GPU-related things like NVIDIA Parabricks, or CPU-optimized things like Sention tooling. So these are all, they're all prepackaged for you. And so all you effectively need to do is tell it, this is where my data lives, run on this data, and then wait for it to finish, and you'll have results. The other piece of the tooling is you can, there's some open source tools that we released alongside of Ready to Run, so that if you have a list of publicly available containers, there's a solution that we published that will go and fetch those and bring them into your ECR repo for you. And so then the only thing you need to do is have a config file or a profile associated with your workflow that will swap out those containers and point them to ECR. Does that help?
Yeah, that's really helpful. Yeah. Like if I wanted to get in here and see how all these are constructed and how they run my own workflows.
There are a couple. So I can point you to that right now. It's actually out on GitHub. Omics tutorials. So all of those, there's a subset of these that are open source. So GTK, AlphaFold, OpenFold, and I'm blanking on the last one. Single cell RNA-seq. Thanks, Sissy. So I'm staring at it right now. All right. So yeah, they're all, those three sets are here. They came from open source origins, and so we wanted to maintain them as open source as well, and just also show how you take things that came from the open source space with a few minimal modifications, how they can run on Amazon Omics. So yeah, these are here are the GTK ones, and so the idea here is that you can take this repository, clone it down, go into the example workflows, and then from here, it's just a couple of command lines. This uses make under the hood to build everything up. But really, all it's doing is I'm reading a list of publicly available containers. I'm pulling them into your account. And then I'm creating the workflow with Amazon Omics, which is what you should be doing right now with this section of the workshop, learning how that's done, and then starting a run with that workflow with some test data. So, and then that tooling that I talked about is also in here. It's up here under. Oh, sorry. This is a link that I know about, but I can. So if you go up to GitHub, this is the repo here. So it's AWS samples, AWS-samples, Amazon Omics, Amazon-Omics-tutorials is the repo on GitHub. So that utility I talked about is under here under utils. It's something I've been calling OMX. So it's short for Omics. I'm a lazy typer, so Omics ECR helper. So it's a simple CDK app that you deploy, and then you can feed it a JSON list of container URIs, and it will pull it down. Okay, so as far as this section of the workshop goes, let's get back into this section. Is about creating private workflows. We didn't build a workshop around Ready to Run workflows, but if you want to learn more about that, we do have a talk from the PM that launched it. Is it tomorrow at 1 or 10? 10. Okay. Okay, so what we're going to do is we're going to go to workflows, private workflows, and then so we're going to create one workflow is kind of a hello world-ish thing, just to show you just the basic steps of how it's done. And then there's another workflow in here that's a little more complicated, and this uses it uses down here it's GATK. So it kind of shows you both practices here. If it's like I'm going to write a workflow totally from scratch, or I'm just going to borrow one and pull it in. So we'll start with the first one here. So the workflow definition is really simple. This all fits in one file. It says hello in 4 different languages, I think, and or maybe just one. Maybe it just says hello. So we'll take it. Comes bundled up as a zip file. So we're just going to download this guy. Actually, I'll do this. I'll save a link instead. Save it here. Okay, so now that I have that, I'm going to go and click on Create Workflow. I'm going to call this, say, Greetings NF. So this is a Nextflow workflow, so that's where the NF comes from. And then we're going to select that definition from local source. So we're going to pull in this zip file that we just downloaded. And then we're going to say this is Nextflow. Just for now, there's Whittle and Nextflow. But these are the two most popular ones that we hear about. You don't have to do this, but I'm just going to do it anyway. So main.nf. So this is the entry point into the workflow. This is the main script. Go next. And in this case, we're going to manually enter the parameters. And so let's see, what was it? Go name, greeting. And then I think the next one was addressee. Okay. Yeah. Great. So this will take a few minutes to do. And while that's going on, you can go ahead and do the GTK one. So that's done. So we'll go back to private workflows. Close this up so we can see things. We'll create a workflow. And we're going to call this one GTK variant discovery. All right. And again, I'm going to go here. I'm going to download this guy. And if you want to, you can open up the zip file, see what's in there. It's a typical Whittle script for GTK, or you can go to this repo that I pointed to earlier. I think one of these workflows is the same one. It might be, probably this one. Probably this one. Something like this. So I'm going to go and select that zip file I just downloaded. And in this case, this is Whittle. And if I'm going way too fast, let me know. Okay. And then here, this one has 15 parameters. I'm not going to ask you to enter those in. So this comes as a JSON template that you can download. So we're going to download this. And yeah, template one. And I'm going to bring that into here. Or the template. Okay. So there's a lot. So there's 2 reads, reference fast days, so on and so forth. Up. Are you on a Windows machine? Can you add the extension back in? Is it just a little thing underneath the box? Or sorry, I think you can go ahead with that. I've had a similar issue. Can you still move forward through the flow, or is it blocking the flow?
Well, we can't upload the file.
You can't upload the file. Period.
But I can try to unzip it.
Can you click next? What happens? Oh, that's left the
Which one is it? The NF, the Nextflow one, or the?
Yeah, it'll be both.
Okay. It should work. I noticed this issue with a customer a while back. It's a weird Windows thing.
I don't think it's doing either. I think there's something weird in browser.
Okay, so one thing I want to check, just to show you, and I realize that we're getting a little tight on time. Okay, so my FastQ import from previously is done. And what I'm going to do is I'm going to go in here and I'm going to take a look at it because this is important for what I'm going to do next. What you can see here is that there are two things that you want to take note of. One, this has this many bases in this FASTQ. So these are genomic bases. This is how we store and compute costs or storage costs associated with sequence data. It's by the gigabase. And the other thing is this Omics URI. So we're going to actually use this in the next step that I'm going to do here, which is run the GATK workflow. Did I do that here? Run it first. So I'm actually going to skip ahead to down here because I want to show you how you can bring Omics URIs into a workflow. I'm going to go back to private workflows. Oh, shoot, I'll do this. So I got my GATK workflow. And we're going to create a run. We're going to go say GATK run 1, fun run. Run 1. In this case, I'm going to use an existing service role. I think there's use a unified job role in this case, simply because this gives you a little more access to other pieces. Nominally, it's going to let you read from any S3 bucket and use Omics storage as a source, as opposed to creating a new one. So when you create a new one, you then have to go back in and edit the IAM permissions to add extra URIs to it. Okay, and so I'm going to set an output location. I'm just going to pick this out, this bucket here that is there. I'm going to click next, and I'm going to, that's new. I'm going to use JSON upload for the parameters. So this is GATK. So I'm going to right click this guy. I'm going to upload those GATK parameters. But I'm also going to edit them. So we're going to go down to here. There's a couple of edits you need to make. One, you need to point to the right containers. So there's going to be two parameter names, one GOTC Docker and one GATK Docker that has kind of a fill-in value for AWS account ID. So we're going to go up into the drop down under where it says WS participant role, and then there's an account ID there. Copy that. And then we're going to go edit value. We're just going to fill that in here. So these are containers that are already in ECR. Okay. And then I am going to point at a FASTQ in the FASTQ files that we uploaded previously, just to show how this works. Right now it's configured to point at FASTQ files in the genome in a bottle, but just to show you how you would do this, you can go to, what I'm going to do is I'm going to open this up in a new tab. So I can keep this flow going. So I'm going to go back to my sequence store, and I'm going to go to find the FASTQ that I uploaded or imported before. So it's this guy here. And then here's this URI. So I'm going to copy this read set URI, and things you'll note, again, this is your account ID, storage, US East, Amazon Omics, or Amazon AWS, sequence store ID, read set ID. That's the format of these Omics URIs. So I'm going to go up in here into FASTQ1, and I'm going to replace all of this with that URI, and I'm going to say, all caps, source 1. Say that. And then for FASTQ2, I'm going to do the same thing. Let's slash all caps source 2. We'll save those edits. Everyone with me? it should be source one. No underscore. So we click next and then go. So this, you don't have to wait for this workflow to complete. This one actually takes 2 hours to finish, and we don't have that kind of time. There is a pre-run workflow that's in here that you can poke around at later. But I wanted to show you what that process looks like to get a workflow running in Omics and nominally looking or pointing to data in Omics storage. Oh, I got to start the run. Okay, so that was probably the more complicated. I jumped ahead to do the more complicated part of the workshop section. So one of the things that folks also asked me is like, how do I know what costs a workflow incur? So if you look into a completed run, so we have one here. This is one we ran as part of provisioning. You should see, click into it and you should see a tasks tab. This only has one, but for normal workflows, you'll see like hundreds, perhaps thousands of tasks. And each one of these things will have resources. And so all you need to do is go down and look at what these resources match with as far as the Omics instance pricing. And it's effectively a table lookup. This CPU memory maps to this Omics instance, and this Omics instance costs this much. And then you can go and add all of that up, and that's the cost of your workflow. You can do that manually, or you can go to a utility. There's a script here in the utils that does that for you. So there's a compute pricing script. It's a Python script. All you do is you point it at a run ID, and it'll do that for you. So it'll go and fetch the public pricing for the region that you're operating in, or whatever that is associated with the profile, that your AWS profile that you're using, and pull that down and match it up with your run. Right. So what you do is you go to runs. If you find a run that has already completed, the details will be there under tasks. These are all the individual compute tasks that executed in the workflow. So you can do this by hand. You can do the costing by hand. It's not that hard, but you can also, there's a script that we wrote that can automate that for you. So it is, AWS samples, Omics, Amazon Omics tutorials, and then there's a folder called utils under that, and then this is a script in there. Yes? So that's a good point. The ready to workflows they're costed by the run themselves. So they are kind of pre-priced. So yeah, so what you see here, that's their cost. So you give it two samples. There are samples that fit within the criteria of the workflow. I think some of them take like there's certain size limits of data files that it'll take, but these are benchmarked to run at this price. So yeah, I think we do. Yeah. Yeah. Sorry, I wasn't sure we had that count, but yeah. So these are kind of these are estimated runtimes. They do vary depending on the amount of data. So okay, let's move on to the next one. I know we're getting a little pressed for time. The next one is probably the most complicated piece, and this is like setting up analytics. So when you finish running a workflow, most cases you're going to generate a VCF file. What do you do with it? All right. So most people want to say, I want to take this VCF file, I want to query it. Query is a loaded term right now. I want to query it, and I want to match that with, say, another database of like, if you see this single letter change in the genome, this potentially causes this mutation, which then causes this disease, which can be treated with that drug. So that's kind of a typical use case. The challenge, of course, is how do you query a VCF file? Okay, one VCF file is not that hard, but let's say, how do I query a terabyte of VCF files? That's a little more challenging. So that's what Omics Analytics is for. So we're going to drop into here, and we're going to do two things. We're going to create a variant store. We're going to create an annotation store. We're going to get some data into those, and then we're going to start querying them. All right? So let's get moving. When does this workshop end? Noon? 12:30? Oh, we got plenty of time. Carl says it ends at 12:30. So we're at 11:30 or 11:40. So I'd say about 20 more minutes. Yeah, 20 more minutes of active build time. Okay, so we're going to go to back to our Omics console. We're going to go under Analytics, and what does the workshop guide say we should do first? We're going to create a variant store. So we're going to go and create a variant. Go to Variant Stores. Oh boy. And click the orange button that says Create Variant Store. I'm going to say my_variant store. And then again, we see reference genomes. In this case, we're going to pick HG38. Continue. This takes a little bit of time. So while that's spinning up, we're going to do the same thing with, we can do effectively the same thing with an annotation store. So we can create an annotation store while the variant store is creating. So annotations, the process is roughly the same. Analytics, annotation store, create annotation store, my annotation store. And this is a slight difference. Annotation stores take multiple formats. You can bring things in as tab delimited or comma delimited text. We've seen annotations out there that are in VCF format themselves. You can also bring in files that are genomic feature format files or GFF files. I'm going to select VCF, and that's because the annotation data I'm going to bring in is ClinVar. It comes as a VCF file. So again, HG38 as the reference, and then we'll create that annotation store. So these take a few minutes to create.
Could you tell us a little bit about what's going on in the background?
Yeah, what it's doing is it's creating some tables that are in it's got a couple of resources that are spinning up. So it's creating some ETL functionality that's there to transform your VCF files or your annotation files into Parquet, and then it'll land it into a data store. That under the hood is, it's backed by S3, but it is, effectively it's presented to you as a queryable object in Athena. So.
Is there access to the underlying?
No, there isn't. So, but it's just how Athena works effectively. It's something. So under the hood we convert it to a format that's more efficient to query via Athena. So it's effectively Parquet, but it helps with large scale queries. So good. Say again? What other types of files? I'm sorry. Other Parquet files? I don't think so at this time, but.
So you can't walk them into the variant store, but if they're actually already Parquet files, you can access them through Athena or
Yeah.
any of the other sort of analytics tools.
Right. So
you would be able to potentially you can bring in more than one database. Could we configure a workflow to export content? You could.
if you wanted to, you could.
You would have to add a state. version of VCS is straightforward. So that's one of the main things we're doing here is the ETL to like mess up because there's a lot of people are curious about using like at that conversion of the ETL, that using leverage of the workflows plug into that. Yeah, so to do that from a workflow, you could add a step in the workflow that the workflow makes a CLI call to the API. So effectively doing what you're doing in the console, but doing it from
Yeah.
a command line.
Okay, so my variant store is up. I'm going to go ahead and import some VCF files into it. So I'm going to go click on that guy, my variant store, and I'm going to click on the orange button, import variant data. Did I say create? Yes, create a new service role. Actually, what I'm going to do, I'm going to say use existing just in case. Select the Omics unified job role, just because this is coming from a different source. There's this link here. This is a set of static workshop, static data sets that we have. This points to this VCF file. So we're going to copy that into the URI. And then we're going to go and create import job. Okay. And then we're going to do effectively the same thing with an annotation store. Oh, these things are big. Create, oh, not create, sorry. So annotation store, import VCF data. I'm going to use an existing role, so I'm going to pick that unified job role. Go next. Where am I grabbing this from? Here we go. And so this is a ClinVar. So this is a ClinVar VCF file. I'm going to copy that. This is what I'm getting. And then create import job. Okay. So these will take, oh, I don't know. I think these are fairly fast to do. And so while those are importing, what we can do is now we can set up the querying mechanics. So all of these things are, so all of your variant and annotation stores are, they're brought into lake formation so that you can, they're governed by lake formation. So AWS Lake Formation is a service that allows you to put permissions around individual tables or columns or rows so that you can effectively meet your privacy and security needs for effectively the very sensitive data of potentially personal genomes. So this is the moment in time where we kind of jump out of using the Omics console and poke at other stuff. And this is kind of important because at this stage, once you have variants in this format, it's less of a genomics workflow and more of a data science workflow. So this is where you can get more heads into the space of analyzing genomic data. So I'm now going to drop out into, sorry, I'm going to open up the lake formation console. So I'm going to go up to the search bar and say lake formation. Kind of open that up in a new tab because I want to keep Omics around. And if you get here, just click Get Started. Most of this stuff should be already set up for you. This is just kind of the initial screens you see with lake formation, set up a data lake administrator and whatnot. Those should already be set up here. There's just a couple of verification steps. So we got here. If we go to administrative roles and tasks, we should see this under data lake administrators. So if you're here, you're good. So the next thing you want to do is now go under lake formation data catalog databases, and we'll just create a database. We're going to call this OmicsDB. And then create database. You know what I'm going to do? I'm going to like stretch this just a little bit more because the nav is getting in the way. That's better. And now we're going to create resource links into that database. So resource links are kind of like, they're like pointers. So these are going to point to your variant and annotation store. So we're going to go to tables. And here, under here, you should see the variant store and annotation stores that you created before. You can use those if you want. There are also pre-created ones with data in there. I'm going to use the pre-created ones just so I can get through. I don't know if my my imports have finished yet. Actually, I can probably check. Let's do this. Probably not done yet. Yeah, it's still in progress. So I'm going to use the ones that were kind of pre-baked. So I have two pre-baked ones here. There's one annotation store. There's a variant store here. So, but the steps are going to be the same. So I'm going to select from these tables. I'm going to select, say, my variant store one, and I'm going to go and create resource link. And I'm going to call this Omics variants. And I'm going to link that into OmicsDB. And that should be all I need to do. And then I'm going to do the same thing with annotations, the pre-baked annotation store. So Omics annotation store 1. So create resource link, Omics annotations, OmicsDB, and then create. Those are pretty fast. Okay, so now that's the minimal amount of setup you need to do in lake formation. So now we're going to jump over to Athena where we can start querying things. So I'm going to go up to the search. I'm going to say Athena. And do a little bit of setup here. We have to create a new work group. So we're going to go to the nav on the side of Athena under administration and work groups, create work group. We're going to say, we're just going to call this Athena 3. Omics analytics stores use the newer Athena engine, so this is important. The default one that your account comes with uses the older Athena engine for the time being. So we're going to go to Athena, work group name is Athena 3, analytics engine. We're going to select manual, and we're going to make sure that this is Athena engine version 3. And we're also going to set the query results location while we're here. We're just going to select this output. And if we want to be pedantic, we can say, we can just attach Athena to the end, just to keep things organized in there. All right, I think that's all we need to do. Yeah, that's fine. Okay, so now we can go into the query editor. So up here under Athena query editor, select our new Athena 3 work group. And you should have a database here called OmicsDB. And then you should see two tables here. So variants and Omics annotations. And so now we're working with SQL now. So what we can do is we can preview this table. So we can say hit the little dots here and select preview table. And this will just fill in a query. And so now I'm querying variants like a SQL table. And so you should see results that come back that is something you can use. You have what you see here. This is the import job ID. So this is generated when you import a VCF file. Each VCF file creates its own unique import job ID. But other than that, the columns should look fairly familiar to you. You have the contig name. So in most cases, it's a chromosome name. You have the position within the genome. that is associated with a variant, and then you have what that variant is, effectively what was the reference, what was in the reference genome, and what were the mutations, or what were the changes to the reference genome. And then after that, you could see other things like quality scores, or other info that came from the VCF file, all here in a table that you can manipulate with SQL. And you should see the same thing if you do similar things if you do with the Omics annotations. So you can go Omics annotations and then preview table there. And so this is again going to be ClinVar. We brought this in before. Very similar stuff since this is a VCF file. This is where it gets a little case dependent. If you bring in a different annotation set, you might see different columns. But in this case, it was ClinVar, it was a VCF file, so it has very similar columns. But again, you see stuff like contig name. Again, it'll be like the chromosome ID, start and stop positions. But then you'll see additional stuff that's specific to ClinVar. So you'll see what database did this annotation come from? What is the clinical significance? Or in some cases, if you can spot it, there might be codes. So SNOMED codes associated with whatever disease this variant was annotated with. And so the power here is now you can take these two tables and you can join them. So they have similar, effectively primary keys of chromosome position ref alt. And you can go and, let's bring this back over here because there's a sample query I have. Down here, you can now drop in a query that looks like this. And to combine your variants with annotations is now just a simple SQL join. So if we run this, this is going to query the annotations that I have compared to ClinVar, looking for variants that are, quote, likely pathogenic. So while this is running, a couple questions. You were first, sorry. Go ahead. Yeah.
Actually, this VCF is not very typical of VCF. The VCF, how we can query the other frequency, like read depth and undo depth in this case?
I don't completely understand. So like if the... Oh yeah, so those are all columns that are there. They might be in the deeper structure within the output. So yeah, keep scrolling. So it's all here in the. You might not see it in this one, but like they're in other VCF files that we have. They'll come through. You'll see like cases. You'll see like all of the annotation, or there's tags in a VCF file that they will get processed out and put into either in information column or the attribute column, somewhere in here. Yeah.
Let's say you have EPD or something.
Mm-hmm. Mm-hmm. That might be something you can talk to later, right? With querying, like just getting more statistical information out of.
Let's say with GenMark, you're looking for,
Mm-hmm.
you want to filter everything that below 50%. And without this one, show everything. You can do in Athena, I mean, there are some complicated queries you can do to generate new values. So it can do calculations.
Yeah.
Similar to what you can do with SQL database. The other thing it can do is if the information you need is buried in one of those arrays or nested structures, Athena has a part of its language is the ability to go into those arrays or into those nested structures and include that in the query.
Yeah, so you create a view, essentially. It will pull out whatever little bit of info if you want to, and make its own column.
Then you have the column between, and then you do the math.
Or you can do a like or something in
Yeah.
And if none of that works, usually you can use SQL.
Oh, do you want to use the mic? I guess people are like.
if none of those other options work, where you can't express it in a SQL arithmetic operation, or you can't extract it using the sort of the parsing tools that SQL offers, you can at least just subdivide a larger data set into a chunk that roughly contains the information that you're looking for, and then download it and process it using your own tooling.
Another question, same thing. That just for one sample, you said you have multiple samples in one piece there. You ask the same question. Give me a variant of this the sample A. I will 10 sample with this other frequency. Not reject, and not reject other frequency. So we're doing the same thing. Like
You can do it against either multiple VCFs or one. Instead of variance per sample, we can do it with multiple sample VCF.
So you can, so part of this is how you want to arrange your data. So you can have a variant store is designed to hold multiple samples. So you can import multiple VCFs into that variant store, and you can then query it. Think of it more like in some ways it's a normalized table where you have just sample ID as the key. So then you can sub-select from that. So if you want to compare two samples that are in the same variant store, you would do two sub-selects to say sample 1, sample 2, and then I want to combine them later on in the SQL query. Or you can have them come from two different variant stores. It really depends on how you want to arrange your data and ultimately what query works best for the question that you want to answer. So from that point, that's why I was saying before, at that point it becomes a data science question. All right, so you had a question? Carl, you want to answer that?
So if you ask a performance question, you always get an "it depends" answer. But the thing that I'll get into when we get into the slides from Bill and I is that it depends specifically on how filtering your data, how much you can apply filtering to the query. So Athena is very good at processing very, very large data sets if you give it very specific filters. If you give it a select star, or if you give it like, give me half of a 50 terabyte data set, it won't finish. It'll time out after 30 minutes.
Okay, so in the interest of time, I want to give some time for Carl and Bill to talk because I think we're getting into those what do you do next questions. But there is another, a kind of a last section of this part of the analytics where, I showed you poking around in Athena, but I know that a lot of folks in bioinformatics and data science in general, they want to live in code, right? So you can do all of this stuff in a Jupyter notebook. So you can query Athena, you can use the AWS SDK for Pandas, and you can pull back a data frame of your results, and then you can do whatever you want with that data frame. So be it develop an ML model, combine it with other data sets, do some visualizations, what have you. And there's a section of this part of the workshop that kind of walks you through what you need to do. And it's relatively simple. Effectively, launch a notebook, install AWS Wrangler or SDK for Pandas, and then query, and then get your data frame and go to town. But I think this is a good segue here to kind of switch over and say, what now? Carl? All right. So let's pull these up. Yeah. I think they were going to turn on the podium mic.
Okay.
let's go here.
Yep.
And then,
This podium is wobbly. Okay, thank you, everybody. And I want to say a special thanks for your time and attention. My name is Carl Goodwin. I am with BioTeam. I'm joined by my colleague, Bill Van Etten. And we're going to talk a little bit about what it's like to use the service for some real use cases. Obviously, the Omics service is actually still pretty new, so I'm not going to tell you 5 years of experience with a service that's been out really only a couple of months. But some of what we're going to talk about is based on real client work. So if you have more questions about the things that I'm going to share, please join us at our booth. We're at booth 608. All right, and catch us there, and we can maybe answer some more questions for you. Okay, so the first main topic that we were presented with a particular client was, okay, Omics seems like a cool service, but we have 115,000 VCFs that we'd like to use. And so knowing the power of Athena and putting a bit of trust in Amazon's ability to work at scale, we started working with the Omics team to design a solution that would work at that scale. We were not engaged with the sequence store or the workflow at that point because the client already had the VCFs. So the first thing that the team kindly requested us to do was to submit a limit increase. So the sort of the default limits for doing work with Omics are enough to get you started, but if you're working at the scale of tens of thousands or hundreds of thousands, it's probably a good idea to increase the parallelism on how many import jobs you may be wanting to run at a given time. And the other major bit of advice that's kind of sensible for anybody who's worked at scale is you want to load data in parallel and in batches. So it's important to note that if you've got a lot of data, you don't want to wait serially. You don't want to have to babysit your own little script in order to deal with that. And you also want to be able to recover from failures. We did have, over the course of loading this set of data, a couple of instances where we needed to pause and address. That was kind of a fun thing when we tripped an internal service limit within Omics, and they said stop. So in order to do this, the solution that we built was to use AWS step functions and Lambda. Obviously, if you've got your own tooling or your own programmers, you can do it however you want. But we found this to be a very good way of effectively processing through tens of thousands of individual tasks working with the Omics service with just a few, the Lambda functions were pretty short, 10, 15 lines of Python code. It's a pretty straightforward loop that if you've built this before, you can recognize that. Although I did find out just today that that they have some integrations with EventBridge, which could even make this this workflow simpler. But again, just for points of advice, don't forget about retry and back off because the service limits will kind of tell you to slow down, and you'll get too many failures if you don't have your own algorithm back off. And then the ability to capture those failures and then retry individual things that have failed is way better than having to go back and double check whether you've successfully loaded data. So as we've talked about, one of the major use cases of dealing with large amounts of variant data and sequence data is to engage with it at a multimodal level, right? And the general outline is that when you have your variant data available in tabular form that's queryable through the Athena query engine, your next major task is to bring any other tabular data to bear on the Athena query engine. And there's a number of different ways that you can do that because Athena is a very kind of well, it has a lot of hooks into a lot of different other sources of data. But the most straightforward one to describe, and the one that we used for this client, was to use glue ETL to convert effectively CSV data into Parquet and put it in S3 buckets that the client controlled, and then to use that lake formation thing that you demonstrated to bring the Omics variant table into the same Athena workspace and an Athena database as the other modality data. So you can load structured data. So if you've got clinical data or experimental data that's already in tabular format, you can load that. When we were working with unstructured data, the general recommendation we found was to load any metadata associated with that unstructured data, particularly any identifiers that relate it to the rest of your problem space, and then also include in your tabular data hyperlinks to the unstructured data that you may have stored in S3 or whatever. And so the critical thing here is that many of these multimodal queries will fall under the category of, do I even have that data or not, right? Do I have an image for a given patient? Because I might have 100,000 patients, but I might only have 30,000 patients with image data. So the ability to say, okay, I've got this set of patients that have this criteria and this set of patients that have this criteria, and kind of grouping all those criteria together into a single operation is the main goal with the Athena engine. So unfortunately, this is an eye chart, and I totally recognize that. This is not something you can run, just cut and paste. But there's basically two sides to this slide. If you know SQL, then please take a picture of that or get the slides later, because this is sort of a very this is a reasonably accurate way to write a SQL query that performs a particular multimodal operation. If you don't know SQL, don't worry about that side of the slide and just focus on this side. I've tried to color code the various pieces of the query so that the the human readable explanation is on the left. So this query is fundamentally, its fundamental goal is to try to do the example that I just said. If we're looking for a subset of patients that meet a certain set of criteria, those criteria are, we have a clinical table that identifies them as having a clinical diagnosis of hip osteoarthritis. We're looking for the patients that also have image data of the hip region. And then we are looking for variants that have been tagged with arthritis. And so we're basically trying to find the patients that we have genomic data that where they may have a variant that relates to arthritis. They have imaging data that we could refer to, and they have also that clinical diagnosis. The last piece to this is basically the connectors that glue these things together. So in this example, the VCFs don't have the patient IDs. They have a different barcode associated with the samples. And so we have another table that maps between the patient ID and the sample barcode, which allows the connection to the genomic data. So again, this is a big chunk, but hopefully what you can see is that there's individual computed tables that then get made available to this final join. And that goes towards my last sort of set of tips or recommendations, is that it's not straightforward to create a query it's not straightforward to create a query that can efficiently process the volume of data that you may load at that scale. And so the recommendations that I have, of course, if the example that I gave helps, that's great, but you're most likely going to, again, because this is a data science problem, you're most likely going to be trying to build the query on your own somehow. And so the major recommendations are to apply as many filters as you can to try to trim down the data to something that the engine is going to be able to handle. From the perspective of the genomics data, the two major dimensions are, If you've got a lot of samples, you want to limit the number of samples that you're considering. And if you've got large genomic regions, you want to limit the scope of how much of that genome you're potentially interested in. So a query that says, give me any patient with this genome could be really too much data. A query that says, give me the entire genome of this set of patients is also potentially too much of a query for the engine to handle. But saying, give me this genomic region with this subset of patients is a tractable query. And in order to get towards that, the easiest way that I found was to break your query into these computed table expressions. So if you're trying to just make sure that you get your query right so that you find just the patients that have the hip imaging, you write that as an individual query, and then you bring that into the final query. You could also write that data to a temporary table. Athena does allow you to build temporary tables using Parquet S3 as a backend, but it also works as computed table expressions. And then going to that performance question, if you run into issues when you are creating this monstrous query, you write what you think is a good query, you submit it, it times out because it's running too slow. The main goal there is to take those chunks and to ensure that each chunk on its own returns at a reasonable time. And I found, a couple of edge cases where I didn't realize that I had misrepresented the join, or the data set was much larger than I had expected it was going to be. And so by breaking it into those pieces, you can troubleshoot and diagnose it in that fashion. I'm going to hand it over to Bill, and he's going to talk a little bit about his experiences.
Hit the arrow?
Yep.
So I guess I should face over here. So I was asked by AWS to kick the tires on this GitHub repository, Omics end-to-end genomics. And looking at this diagram, essentially what it does is it gives you code to stand up a CloudFormation stack that will do all the stuff that you did manually in essentially hitting the return key. So I was intrigued by that. And the first time that I did everything that you did today was 5 years ago, before Omics existed, shortly after Athena was released, and did it all by hand. And it was hard and laborious. So I like this because it's so easy. So when I decided to kick the tires on it, I had gotten my genome sequenced, I don't know, about 4 years ago. It's been sitting on my desktop. I haven't done a damn thing with it. I'm a geneticist. I'm too busy doing everybody else's stuff. So I thought, so it was built on HG19. I thought it'd be a fun experiment to rebuild my genome on HG38. So essentially what you do is you download this repo. You create a bucket where it's going to store CloudFormation artifacts, and you run the command upload artifacts, which sends it all up to that bucket. Then you go to the AWS console, and you'll see the stack there. You have to give it 2 buckets, one where your fast queues are and where you want to put the results, and you press go. 30 minutes later, you have a CloudFormation stack that you can drop fast queues in a bucket. It'll spin up all the resources that are necessary, do the alignment, do the variant calls, create the sequence stores, annotation stores, workflow runs, and give you an Athena query interface to all that results. So the part I want to tell you is the part that was hard, even with this. So I tried this shortly before, shortly after Omics was publicly released. So the problems that I ran into might be gone now, but I thought it would be useful to share with you the problems that I had, so that if you run into those problems, they won't surprise you. So the first one was uploading the fast queues from my laptop, which, if you're in a research center, this is probably trivial, but so I used, if you upload, I forget exactly how big my fast queues were, 200 gigs or something. If you try to upload that, it takes several days, over 5 megabits up on a cable modem. and invariably it fails, and you're pissed off because you waited 5 days to find out that it failed. So I just used the old timer trick of using split and cat. So I chunked it up into 100 megabyte pieces, then used AWS Sync to pull it up, and a couple of them failed, but then you just run it one more time, and then 2 seconds later it's up. So that was a useful trick, an old timer trick. Then the other thing that I ran into was I'd also been doing a lot of omics research for another customer, and I'd created a lot of reference stores. So when you run this, it tries to create a HG38 reference store for you, but there's a limit to how many that you could have. So I'd already exceeded that limit. So the first time I tried to run it, it says, nope, can't do it. You have too many reference sequences. And then there's no way to delete reference sequences from the console. The only way you can delete them is through AWS CLI, which the one AWS CLI that I installed using Homebrew didn't know anything about omics yet. So I had to use Homebrew to delete AWS CLI and then download the package installer that they provide. And then, it's a little bit tricky, a couple of commands to delete the reference store, but I was able to delete them. I went to run it again. Then it failed again because my FASTQ names were in the wrong format. So, in this pipeline, they expect you to have the FASTQs in a particular named format. So just renaming the files fixed that problem. Then the third thing I ran into was the number of state transitions. So as it's going through this big workflow, it's constantly polling, and every 30 seconds it was checking on something. But it ran long enough that I hit the maximum threshold of state transitions, which I think was like 30,000. So then I tried to use this other GitHub repo put out by AWS, this resume from any state, thinking I could pick up where I left off, which is, it works for certain kinds of failures, but not exceeding a threshold sort of failure. So that didn't work. So I had to start that over again, but I had to increase the polling intervals in the stack. So I had it check once every 3 minutes instead of every 30 seconds, and the problem went away. And then after, if you use that 100, the 1,000 genome sample, it takes about 4 hours to run. But if you run, my whole genome took closer to 30 hours to run. Anyway, so those are the tricks that I wanted to put through. But the thing that I thought was interesting is, I got more time? Yep. So another project that I worked on ages ago, and I can tell you about it because it's published in Nature, but we were doing whole genome studies on 10,000 patients with autism. We found 18 candidate genes. So Bioteam had to build this whole infrastructure to do all of this. And so right after Athena came out, I thought, wouldn't it be clever if we just got rid of the computers and we just ran it on a static website? So what scientists wanted to be able to do was have a web interface where they could plug in genes and phenotypes and genotypes and positions and query, and then join ClinVar with their variants, as was showed earlier. So I wanted to do that in a static S3 website, and made this simple app to do the same thing with zero infrastructure. So this is so small I can't see without peeking around. But this is a static JavaScript website. Altogether, it's probably 50 lines of code. This is just super, super simple app. Pulling out the stuff researchers wanted to enter, which is the JavaScript is coming up with the SQL that gets passed to Athena, which returns the results in the web UI, giving you the variance resulting from your query that can then give you links out to the UCSC browser, MCBI, or PDSNet or something. So I put this up because that's the value of being able to do SQL queries, joining your variants and annotations. And that's what the clever trick is to provide. So I think that's all I wanted to talk about. We're at booth 608 if anybody wants to talk to us. Any questions? No? Okay, thanks.
Okay. All right. Thanks, Bill. Thanks, Carl. So that's about all we have for the workshop. I want to go through a couple of testimonials. We certainly have a number of customers using Omics today. There's a few that I want to highlight. First is CHOP. And so they are, if you don't know about who CHOP is, Children's Hospital Philadelphia, they are a U.S. hospital. It was the first one devoted to exclusively to the care of children. And they have been using, they were one of our first customers to use Amazon Omics. And they've been using Omics to store and analyze tens of thousands of variants so that they can provide a comprehensive view of all of their patients, all the way down to the DNA. So this is kind of in one of those use cases that that Carl was talking about, like hundreds of thousands of VCF files across their whole patient cohort. Second is Element Biosciences. They're a sequencing provider, or the sequencing instrument provider. They actually have a system called Avidi. It's a modular, high-performant DNA sequence platform. And you'll see actually some of their workflows related to this platform, to their platform, in Ready to Run. So they wanted to use Omics as a way to lift up their customer base from having to run specific workflows to process data that comes off of their systems. And so this enables them to do this without the need to set up any infrastructure of their own, and both Element and their customers, so that both of them can focus on their differentiating research. And so finally, there's C2I Genomics. They are empowering researchers and physicians and patients with ultra-sensitive whole genome cancer detection. And so they have a software as a service solution to perform cancer tumor burden monitoring at a global scale. So, and they leverage thousands of human genomes or genome sequencers installed around the world. And so they're using Omics in a way to scale out, like where their workflows get run. And how efficiently they can deploy new analytics to the cloud. Okay, so finally, where do I start? Actually, before I do that, I think one thing that we forgot to talk about was like, well, what did we build today, and then how much did it? Quick recap. Sorry, we did this. So we went from raw sequence all the way to queried variants in about an hour. Yes, it was a little bit tight, but I think it's evident that there is a lot of power in and uplift that Omics provides. It lets you to get from a raw sequence to something that you can start doing scientific interpretation on within an hour. And overall, if you let that GATK pipeline finish, we had a question about cost. Overall, this is how much this workshop costs today. It was about $1. So all the sequences we stored, and if you let that workflow run to completion, which was about 2 hours, and then the variants and annotations we stored, reasonably affordable. And ultimately, we talked about other parts of like what Omics can enable you to do. So overall, it's part of a suite of other tools and purpose-built services from AWS. So Omics sits alongside things like Amazon Health Lake for clinical records, and medical imaging, and Amazon Comprehend Medical, and for applying NLP, natural language processing, to clinical notes, and then Transcribe Medical for automated speech recognition. And all of this stuff, like as we showed earlier, is you can combine it to create these multimodal analyses. So clinical records, omics, imaging, all of this can feed into infrastructure, analytical infrastructure on AWS, where you can bring either additional analytical services, so EMR, or Amazon Elastic MapReduce, or for big compute, or you can bring dashboarding tools like QuickSight, or you can bring it into Amazon SageMaker to do machine learning and AI, or you can bring your own tools. It's all there for you to build what you need to build to make the scientific discoveries you need to make. All right, so with that, where do you learn more? This is where I got to. Where do we start? Well, first off, reach out to us. We're here to help. If you have any other questions after this workshop, you have a couple of faces you can wave down on the expo floor. Apart from that, we also have a number of partners. We have BioTeam speak with us today, but I believe also a number of them are around BioT as well. And then finally, if you're the DIY type, we have plenty of documentation out on the web. So there's our developer guide, learn about the nitty gritty about using Omics, and finally our webpage for additional web cases or use cases and customers. And that there's a couple more links that we can point you to for more stuff about AWS and genomics and healthcare and life sciences and open data, other solutions that you can deploy via our marketplace, other partners you can pull in. And finally, I mean, that's a wrap.
I just want to make one comment. So the 3 components that you saw in Omics, it's not an all or nothing deal, right? So you can, if you are interested in storage and that's your use case, you can only use that. And let's say you don't have a need for the others. So you can use those individual pieces. Yep. And of course, if you have an end-to-end solution, they're better together, right? So,
yep.
Thank you.
Thanks. And one last ask. That's a survey link. Let us know how this workshop was, so we can improve it in the future. So. All right, any lingering questions? Sure.
What is the storage, the compression efficiency between S3 and the sequence store? And if that can't be answered, what is the storage savings for comparable set of reads?
I can't answer the compression one, but the savings is, we're working on a price calculator that kind of works through like the comparison between like just S3 versus Omics. What you get is effectively something that's akin to like using Glacier. So it's that level of savings in Omics.
Yeah, so we've seen about up to 60% based off of how frequently you access it when comparing to S3 intelligent sharing.
So that's a big deal.
And it has that intelligent sharing built in, so you get the benefit not only of the compression, but also of the discount for when you don't touch it.
Yep. In the back room.
Regarding the ready-to-run workflows, is there a process that Amazon partners with external partners to expand that library, a publishing mechanism, and is that vetted and maintained over time?
Yes. Yes, yes. There's a program. If you do have workflows that you want to publish with us, just let us know. And yeah, there's a programmatic way to get that in. Another question?
For the like loading of data from these genomic stores, the way that they're transferred is in a stream. So do all the downstream processes need to be able to accept like a stream of data in order to function, or are they able to say download, you know, the FASTQ, operate on it, which is like the traditional model, whereas you would maybe be able to stream it and save some of that overhead?
Sorry, is that in reference to the workflows piece?
Yeah, so like, for example, in a liner, if you could stream in your FASTQ, you wouldn't have to download and then start from the download stage.
If you have tooling that can support it, I think you can do that. Right now, what we do is we, for all workflows, for a workflow run, we recognize that there are efficiencies to be had to have a shared file system across all tasks. So that's part of the starting workflow process.
So for those ready-to-run workflows, I noticed you guys have tools like KTK or Synthans. Do users have to care about their license?
Yeah, yes, you do have to. So with Sention, with any licensed ready-to-run workflow, you can bring your own license. So if you have one, you can use that. The only thing you need to do is just let Sention know. So it's like, What you do is, at least the process I'm aware of today is you contact Sention, they'll ask you for your account canonical ID, and there's instructions on how to get that. And then they can link that to your use case.
One other caveat on that, Sentinel has graciously offered all AWS customers a 2-week free trial. So if you haven't, don't yet have a license, then you can use it to run workflows on your account for up to 2 weeks. It's a pretty amazing offer.
Yeah, that's cool. Do you want to go or do you want to go first? Go ahead.
Is there a way for your workflow to depend on custom libraries? What if I want to use, for instance, EP? Is there a way to handle that?
That's an it depends. I think we'll need to talk a little bit more detail. So there you can use like the VEP tooling as itself and then talk to, say, a predefined cache. So if you have that cache sitting in S3 or other storage mechanisms, you can effectively call that, say that that is an input to your workflow. And then once you get to that step of the workflow with VEP tooling, it'll use it. So, but then there are potentially other use cases that we should probably dig into. Yeah. It depends on which one. So there's like the ones that are based on open source. Yeah, they're out there. We put them up in our tutorials website. There is a set there that are they're proprietary, so they're published by our partners.
Just a reminder, I hate to cut you off, I know there's more questions. There is, let's see, there are other workshops, there's other ones at 1:45, if you wanted to register from, you can do that at the desk. There's a extraordinary keynote speaker is at 4 o'clock, room 304 and 306, and then there's a welcome reception, and you set the call at 5:45. All right, have a great day.
Awesome. Thank you very much, everyone. Thank you for your time.
Thank you.